Every second, the Earth intercepts 173,000 terawatts of solar power. That volume is 10,000 times greater than the total power consumption of the entire human population. This creates a massive discrepancy. If we are surrounded by 10,000 times more free energy than we could ever use, why doesn't solar power run the entire world today? There are political factors at play, and businesses that lobby to maintain the status quo. But the most immediate scientific barriers are physical and logistical. The primary tool for overcoming these barriers is the solar panel, the technological bridge that converts raw sunlight into usable electrical energy. To understand why we can't simply capture all that abundance, we have to look past the surface of the panel and examine its subatomic limitations. Solar panels are made of units called solar cells, and the most common of these are built from silicon. It is the second most abundant element on Earth, found in massive quantities in the planet's crust. Inside a cell, a slice of this crystalline silicon is sandwiched between two conductive metal layers. In this natural state, every silicon atom is connected to its neighbors by 4 strong bonds. These connections keep the electrons in place, so no current can flow. In this rigid lattice, the silicon acts as a dead atomic cage. Turning this dead silicon into a functional power generator required brilliant engineers to deliberately introduce specific, microscopic imperfections into that rigid atomic structure. This is achieved through the p-n junction. Engineers create an n-type silicon layer with extra electrons and a p-type layer with empty holes. When these layers meet, electrons wander across, creating opposing charges that form a built-in electric field. Energy enters the system as a continuous stream of photons, tiny particles of light shooting out from the sun. When a photon strikes the silicon cell with enough energy, it knocks an electron from its bond, leaving a hole. The electric field at the junction ensures these freed particles only go one way, the electron to the n side, the hole to the p side. Thin metal fingers at the top of the cell collect these mobile electrons, funneling them away from the silicon. The electrons then flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back of the cell. One individual silicon cell puts out half a volt. To power a house requires massive solar arrays. This is a remarkably efficient mechanical design, because electrons are the only moving parts and they eventually return to where they started. There is nothing to wear out. A solar cell can generate power for decades. If the solar engine is practically immortal and the fuel is infinite, what remains to prevent total global reliance? At the micro level, we face efficiency losses. Energy is lost if sunlight reflects off the panel or if a dislodged electron falls back into a hole before it can complete the circuit. While the most advanced experimental cells have reached 46% efficiency, most commercial systems currently only convert 15 to 20% of available sunlight into electricity. There are also macro-level logistical hurdles. Solar energy is inconsistent and unevenly distributed. Yields drop significantly on cloudy days, at night, or in high-latitude regions. Moving past these inconsistencies would require massive infrastructure investment, including efficient transmission grids to move power from sunny regions to cloudy ones, and high-capacity storage. Powering the entire world with today's technology would require a massive footprint. Estimates range from tens to hundreds of thousands of square miles of panels. That is a manageable fraction of the Earth's surface. For context, the Sahara Desert alone is over 3 million square miles. Innovations like floating solar farms are also changing the landscape, allowing us to bypass land requirements by deploying arrays on bodies of water. For people without a reliable grid in developing countries, solar energy is already a safer, cheaper reality that replaces dangerous fuels like kerosene. Building a world powered entirely by the sun requires significant funding and infrastructure, but the physics of the silicon cell are already proven, and we are steadily closing the 10,000-fold energy gap.